One of my favorite ways to study metabolism is to do some ATP accounting. Basically, choose a molecule, choose a pathway, follow the molecule along the pathway, see how much energy it takes you in the form of ATP equivalents or how much you generate in the form of ATP equivalents, both directly as well as indirectly. So consider how many NADH and how many FADH2 you're making or you're using, and then what would the consequences of that be if you were to, say, take things through oxidative phosphorylation? So it's not so much that the absolute numbers of ATP and the absolute numbers of NADH and the absolute numbers of FADH2 and NADPH and all this stuff matters. That's actually going to vary, and it depends on how efficient the processes are and which versions of enzymes things use and where things are happening and what tissues and all this stuff. That's not the point. The point is to get you to actually track the molecules through these pathways in order to understand the pathways and in order to gain some deeper understanding of some of the fundamental principles of metabolic pathways. What types of reactions are going to give you energy, which are going to cost you energy, how efficient are various processes, et cetera, et cetera, et cetera. So here's a worked example of fatty acid catabolism. So the breakdown of fatty acids. I'll post a link to the worksheet for you so that you can try it out yourself. And then when you're ready to check your answers, you can come and watch this video, or you can follow along with the video, whatever suits your fancy. We're going to look at the complete oxidation of palmitate, so a 16O fatty acid, as well as a 17O fatty acid. So a fatty acid with an odd number fatty acid, as well as our kind of like default fatty acid, this even number, saturated 16O fatty acid that we call palmitate. No matter what fatty acid we have, well, as long as it's within the normal length range, I'm not going to go into that here. But if we're doing our typical beta oxidation of a fatty acid, that's taking place in our mitochondria. And what it does is it takes a fatty acyl-CoA. So it's a fatty acid, but it's not a fatty acid anymore because the acid part has been swapped out for a coenzyme A. This fatty acyl-CoA is then going to get broken down in cycles of beta oxidation. As the name oxidation suggests, this is going to be an oxidative reaction. If we're oxidizing our fatty acid, we're going to be reducing something else. In this case, we're going to be reducing NAD plus and FAD to give us NADH and FADH2. We're also going to be doing this in cycles. So each cycle, we're going to be cutting off an acetyl-CoA, generating an NADH, and generating an FADH2. So if we go and we look at our kind of like accounting tables, the way I have this set up is that you think about some process, then consider the amount of NTP. So this could be ATP, GTP, UTP, CTP. All of these are kind of interchangeable within your cells. So even if we directly make a GTP, we can still consider it like an ATP. This is important because in things like our citric acid cycle, some of the isozymes, so some versions in some tissues or in some animals are going to make GTP, whereas others make ATP. And so for the purposes of this, we're going to consider them equivalent. For each cycle of beta oxidation, we now want to consider, okay, well, do we generate any of these? Do we require any of these? So starting with these first two columns, or like after this one, we're going to say, okay, we are going to generate an NADH. So we are going to generate an NADH, and we're going to generate an FADH2. Okay, we're not going to require any of these. So now if we were to think about, well, how many potential ATP did we get? Well, we didn't get any directly, but if we were to take that NADH and we were to take that FADH2 through the electron transport chain, what would we get? You'll see different estimates depending on where you look. And again, it depends partly on the conditions. For example, how tight is the coupling between the gradient and the production of ATP? Is that gradient being used for other things? Is it leaky? All this stuff. But if we consider kind of like the maximum, the normal, what we're going to consider is, I like to consider 2.5 for NADH and 1.5 for FADH2. Sometimes you'll see it rounded to 3 and 2, but the way that I get 2.5 is that for each NADH, that's going to come in at complex 1. That's going to pump out 4 protons in complex 1, 4 protons in complex 3, 2 protons in complex 4, for a total of 10 protons pumped out, and it takes about 4 protons per ATP made. 3 of them directly to make the ATP, as well as a 4th to bring in the inorganic phosphate so that you can do this process yet again. Okay, so we have 10 divided by 4 is going to give us 2.5 ATP per NADH, and we have 1 NADH. And so this is going to give us a total of our 2.5 ATP potential from 1 NADH. We can do the same thing for FADH2. In this case, what happens is that although this isn't using complex 2, because remember complex 2 is our succinate dehydrogenase, when you have FADH2, there are other ways that it can pass to Q. And so you're going to pass from that FADH2 to Q. This is going to give you 1.5 ATP equivalents because you pump out 4 protons, 2 protons, 6. Unlike the 10 you got if you went in that complex 1, you get 6 divided by 4 is 1.5. So again, we can then take this and multiply by 1.5, and now we've got our 1.5. If we think about the total potential ATP, we don't generate any directly, but if we were to consider the oxidative phosphorylation, now we have 2.5 plus 1.5 is going to give us our total of 4 potential ATP. But that was just for one cycle of beta oxidation. If we consider a 16 carbon fatty acid, how many cycles are we going to have to go through? So remember that each cycle we're cutting off 2 carbons, not including the carbons on the CoA. 2 carbons, and we have 16 carbons, so that's going to give us a total of 8 acetyl-CoA is going to be what we're going to generate. But to get 8 acetyl-CoA, how many cycles do we have to go through? Think about an apple. If you want 2 slices of an apple, you have to make 1 cut. If you want 8 slices of an apple, you have to make 7 cuts. Similarly, if we want 8 acetyl-CoA, we're going to have to go through 7 cycles of beta oxidation. So 7 cycles of beta oxidation will give us 8 acetyl-CoA. Okay, so we need to do this 7 times. So we have our 7 beta oxidation cycles. And so what we're going to have is that for each of these cycles, we're going to have 1 NADH. So 1 times 7, that is going to give us our 7. And then we have 1 times 7. And yet again, this is going to give us our 7. Now, if we consider how much of the ATP, we just have to multiply each of those by our, we have to multiply the NADH by 2.5, the FADH2 by 1.5. We add those together, and voila, we get a total of 28 ATP. Note that all of this ATP, however, is coming from oxidative phosphorylation. It's not directly coming from the beta oxidation. Okay, now let's consider the carbons that we left, because we still had a lot of potential. Remember that for complete oxidation, we want to oxidize everything to CO2, but we still have acetyl-CoA. We know what we can do with acetyl-CoA. We can put acetyl-CoA through the citric acid cycle, our tricarboxylic acid cycle, our TCA, our Krebs cycle, whatever we want to call it, we can put that acetyl-CoA into it. So we start with our fatty acid, we break it down to beta oxidation. That's going to give us our acetyl-CoA. So acetyl-acetyl-CoA, that's basically just the 4 carbon part before you cut it in half. There are other things that you can do with that 4 carbon part, like make cholesterol, make ketone bodies, but we're just going to consider going all the way to acetyl-CoA. And if we go all the way to acetyl-CoA, now we can enter the TCA. When we enter the TCA, we basically join that acetyl part of the acetyl-CoA with oxaloacetate to make citrate, and now we go around the cycle. For each turn around the cycle, we're going to lose 2 carbons. So in the first turn of the cycle, it's not actually going to be the carbons from the acetyl-CoA that you just brought in that are lost. It's going to be carbons from previous acetyl-CoAs. But on that, basically, it's going to take you 1 cycle to lose 2 carbons. And so we can consider that we go 1 time around the cycle per acetyl-CoA. For each turn around the cycle, let's think about what we have. We generate 1 NADH here at this isocitrate dehydrogenase step, another at this alpha-ketoglutarate glutarate dehydrogenase step, and a third at this malate dehydrogenase step. So if we consider our NADH, we're going to be generating 3 NADH per turn of the citric acid cycle. What else are we generating? Well, we're going to be generating an FADH2 at our complex 2, our succinate dehydrogenase step. So 1 FADH2 per turn of the citric acid cycle. We also make an NTP. So this could be GTP or it can be ATP depending on the tissues, depending on the organism, etc. But remember, those are basically equivalent. So for each turn of the cycle, we get 1 NADP, 3 NADH, and 1 FADH2. Now let's multiply the NADH by 2.5 and the FADH2 by 1.5. And what we end up with is that we're going to get 7.5 ATP from the NADH, 1.5 from the FADH2, and then we get 1 from the NTP. So combined, this is going to give us a total of potential of 10 ATP per turn of the citric acid cycle. Okay, so that was per turn, but how many turns are we going to have to go around? We had 7 beta oxidation cycles because we made 7 basically cuts of that fatty acid to get 8 pieces. But each of those pieces can go through the citric acid cycle. So we're actually going to have 8 turns of that citric acid cycle per our palmitate. So we're going to multiply everything by 8. So we should end up with 80 ATP. And in fact, if we go and we work out the numbers, what we'll find is that we do indeed end up with our 80 ATP. 60 potential from the NADH, 12 from our FADH2, and then directly what we generate is those 8 from substrate level phosphorylation at the succinyl-CoA synthetase step. All of our other steps, however, we're going to be requiring the electron transport chain and oxidative phosphorylation. Okay, so that's a breakdown of the fatty acid, but that's assuming that the fatty acid starts actually not as a fatty acid, but as a fatty acyl-CoA. So that's assuming we have a fatty acyl-CoA, not a fatty acid, and it's assuming that basically we're in the mitochondria, which is where we break down fatty acids through beta oxidation. However, we have to basically get that fatty acid, turn it into a fatty acyl-CoA, and we have to get that fatty acyl-CoA into the mitochondria. So we have 2 things that we need to deal with. One is the activation of the fatty acid to a fatty acyl-CoA, and one is getting that into the mitochondria. Let's start with the activation of the fatty acid to a fatty acyl-CoA. So in this case, we have palmitate, and we want to turn it into palmitoyl-CoA. The way that we're going to do this is with fatty acyl-CoA synthetase, or ACS. This ACS is embedded in the outer mitochondrial membrane, and what it's going to do is it's going to take a CoA, take that fatty acid, take ATP, and basically plop that CoA onto the end of the fatty acid. And the way that it's going to do this, it's actually going to take ATP and turn it into AMP. So typically we take ATP and we turn it into ADP, but here we're taking it to AMP. So it's kind of like we're using 2 ATP. So if we think about what we're kind of requiring, we're going to consider this as 2 ATP equivalents because it would take you the equivalent of 2 ATPs in order to regenerate ATP from that AMP. So if you just want to ADP, you could regenerate it with just the equivalent of 1 ATP, but because it's AMP, now it's kind of the equivalent of 2. So we'll consider this like 2 ATP equivalents. No NADH, no FADH2, none of that stuff involved here. So on net, this is going to basically cost us our 2 ATP. Okay, so now we have this fatty acyl-CoA, and we want to get into the mitochondria because that's where beta oxidation occurs. The way that we're going to do this is through our carnitine shuttle. And so basically the carnitine shuttle, it's going to take that fatty acyl-CoA, and it's going to take the CoA that you just put on, that you just took energy to put on, and it's going to swap it for a carnitine. And then you get a acylcarnitine, fatty acylcarnitine. That fatty acylcarnitine can then get into the mitochondria where it's converted back into a fatty acyl-CoA. Don't worry, this actually isn't going to cost us any energy. Because that CoA linkage is so labile, it's so easy to kind of make and break and kind of energetically swappable. You can swap it for a carnitine, take that carnitine, that fatty acylcarnitine into the mitochondria and swap it back. So no energy involved here. It's just important to kind of remember that you do need this step. And that basically the energy was invested beforehand, but now you can bring it in. You can't bring it in unless you first invest that energy. And then you can't break it down unless you actually bring it in. The key regulatory step of this is this CAT1, this carnitine acyltransferase 1, that does a swap from the fatty acyl-CoA to the fatty acyl-carnitine in your outer mitochondrial membrane. This enzyme is actually inhibited by melanoCoA. MelanoCoA was basically one of the products of fatty acid synthesis. So one of the intermediates of fatty acid synthesis is melanoCoA. It's like the activated acetyl-CoA that you link together. So if you're making melanoCoA, that indicates you're making fatty acids. If you're making fatty acids, you want to inhibit the breakdown. You inhibit the breakdown by inhibiting that CAT1. But that was just a side note. Now back to our regularly scheduled programming. Okay, so we've looked at all the steps, and now let's combine it. So we need to think about if we want to oxidize palmitate, the first thing that we need to do, so we're considering we have palmitate in our cytoplasm. How are we going to actually break it down? The first thing we saw was that we needed to activate it into a fatty acyl-CoA. So what we're going to do is we're basically just going to do this step that we had up here. And so we could just copy and paste into here, or I have it pre-filled out. Basically, you're going to need 2 ATP for that step. What about our carnitine shuttle? This was a simple one. We said this wasn't going to cost us anything. Now we have our beta oxidation per palmitate. So we already did the hard work for this. We saw that we need to go 7 beta oxidation cycles. So we just copy this number into here. And voila, we see that we're going to get 28 ATP from that process. What about from the citric acid cycle? Well, here we did this hard work too. That was where we're going to get our 80. And if we take the net sum of all of this, add up all those NTPs that we generated directly, so that was the 8. We add up all those FADH and those NADH, FADH2 and those NADH, so we had 31 NADH, 15 FADH2, for a grand whopping total of 106 ATP that you could get from that palmitate. Now let's consider a slightly harder situation. Let's consider an odd chain fatty acid, a 17O fatty acid in this case, so just 1 carbon longer. If it's 1 carbon longer and we did 7 cycles of beta oxidation, what would we be left with? Before, if we had 16, we'd be left with nice even number. We'd be left with 8 acetyl-CoAs. Each acetyl-CoA, remember, is 2 carbons plus the CoA part. But if we just consider the acetyl part, 2 carbons. If we were to do the same number of cuts of our 17O fatty acid, we would be left with 7 acetyl-CoA, 14, and then 1 propionyl-CoA, so a 3 carbon product, this propionyl-CoA. So if we say, you might say, okay, well, why don't you do 8 and then be left with 1 carbon? Well, that's not what we're going to do. That's not what your body does. Instead, your body does it where you cut and you have a 2 and a 3. So our carbon products of oxidation are going to be, we have our 7 acetyl-CoA, and we're going to have our 1 propionyl-CoA. So remember, that is going to be our 3 carbon. Okay, so now that we have this, we're going to need to consider what we're going to do with that 3 carbon. We'll come back and deal with the acetyl-CoAs, but we know how to deal with the acetyl-CoAs. In fact, everything else about the breakdown of this fatty acid is going to be the same. We just have to think about the propionyl-CoA, as well as the fact that now we have 7 acetyl-CoA instead of our 8. Okay, so what are we going to do with that propionyl-CoA? What we're going to do is we're going to convert it to succinyl-CoA. We can convert it to succinyl-CoA in a couple of steps, the first of which is going to actually need ATP. So this propionyl-CoA carboxylase is going to carboxylate it with the help of ATP. You're going to then go through some interconversion steps. Pretty cool stuff. It actually is one of the 2 enzymes in your body that actually needs vitamin B12. Fun story. But end of the line, you take this propionyl-CoA and you make succinyl-CoA. And well, we know what to do with succinyl-CoA. We can take it through the TCA. So if we have our odd chain fatty acids, we can make succinyl-CoA. We can enter the tricarboxylic acid cycle and generate ATP. Or we could generate other products if we wanted those other products. So one of the nice things about succinyl-CoA is that it's actually glucogenic. What this means is basically we have an anaplerotic reaction here. We're regenerating a cycle intermediate. With acetyl-CoA, we are only putting in 2 carbons. For each turn of the cycle, we got rid of 2 carbons. And to actually bring the acetyl-CoA in, we had to already have oxaloacetate present. If we want to, say, make glucose, we take malate out of the mitochondria and convert it to oxaloacetate that we can use to make glucose through gluconeogenesis. If we do that, however, we can't get oxaloacetate, so we couldn't bring in an acetyl-CoA. So we can't sustainably make glucose from even chain fatty acids that just generate acetyl-CoA. So we say those are not glucogenic. However, if we have an odd chain fatty acid, we can get succinyl-CoA. Succinyl-CoA. Now, if we bring in succinyl-CoA, we're bringing in extra carbons. Succinyl-CoA is going to have 4 carbons, 3 from the propionyl-CoA, as well as the extra that we added from carbon dioxide. This is then going to give us 4 carbons. If we have 4 carbons, we could then take out a 4-carbon malate, and the cycle could still continue because these were extra carbons that we added in. So those odd chain fatty acids can be called glucogenic. So again, it's not that you can't get fatty acid carbons incorporated into glucose, but you can't sustainably make glucose just based on those even chain fatty acids. However, you would be able to do that from odd chain fatty acids. And you also have to consider that if you're breaking down like fats, so triacylglycerols and stuff, you're also going to get the glycerol that can be used to make glucose. So those parts of it could be glucogenic. But getting back to our regularly scheduled accounting program, let's get back to what that conversion of propionyl-CoA to succinyl-CoA is going to cost us in terms of energy. We see here that's going to cost us an ATP. So if we go to our required column, we can say that we're going to require 1 ATP. No NADH, no FADH2, none of that stuff involved here. So on net, we're going to basically need 1 ATP in order to do this conversion. However, once we do this conversion, now we have succinyl-CoA. And succinyl-CoA, we were just talking about, can enter the TCA. If we enter the TCA, we're interfering at this point. And now we have to consider how much energy we can get. Well, how many turns of the cycle are we going to go around? If we think about succinyl-CoA, it has 4 carbons. We say that each turn of the cycle, we're going to lose 2 carbons. So we need to go 2 full turns of the cycle. But the turns of the cycle are basically the parts where you lose carbon are on this right-hand side of the cycle. And we're right here. If we want to get back to that point, we're going to have to go through these interconversions. And the second half of the cycle, we're actually going to generate an ATP or GDP. We're going to generate an FADH2, and we're going to generate an NADH. This then gets us to oxaloacetate, and now we get to go through the cycle 2 full times. So if we think about the number of cycles, it's kind of like we're going through this about 2.5 cycles. So if we're going through this about 2.5 cycles, well, for the 2 full cycles, we're going to generate 3 NADH, 1 FADH2, and 1 NTP per cycle. And then we have to consider the extras we get. So if we think about this like kind of partial cycle we get, we're going to generate the NTP here, the FADH2, and the NADH here. We're not going to get these 2 NADH, but we're still going to get this one and this FADH2 and this NTP. And so if we go and we add all of this in and we do all of our math, considering 2.5 ATP per NADH, 1.5 for FADH2, we get that we can get 25 potential ATP from this process. We're only generating 3 NTP directly, but thanks to our good old ox-phos, we can get a lot of energy from those NADH and those FADH2 that we're going to generate. Okay, so if we basically combine those two, so we combine that we have to convert to propionyl-CoA to succinyl-CoA and then oxidize that through the TCA and our oxidative phosphorylation. What we're going to get is we have 25 minus 1. This is going to basically give us 24 ATP on net. And now let's combine it all. So we have our activation of our fatty acid to our fatty acyl-CoA. So this is going to be the exact same thing as we did before. This part's not going to change, and the carnitine shuttle is not going to change. So this fatty acid activation is going to basically cost us the equivalent of 2 ATP. And then the carnitine shuttle, well, that was our freebie. It's important because we need to get the fatty acyl-CoA into the mitochondria to be broken down, but it's not going to cost any energy because we already invested the energy at this ACS step. Now that we're in the mitochondria, we can do the beta oxidation. Just like before, we're going to do 7 beta oxidation cycles. So our math for the beta oxidation is going to be just like we saw before for our palmitate, for our 16O. And that's going to give us, allow us to generate 28 ATP if we take oxidative phosphorylation into account. Now the citric acid cycle. Well, for the acetyl-CoAs, how many turns of the cycles are we going to have for the acetyl-CoAs? In this case, we had 7 acetyl-CoAs because we were going to get that 7 acetyl-CoAs and then the 1 propionyl-CoA. Before, we saw that if we wanted to do palmitate, we were going to have 7 beta oxidation cycles, and that would give us 8 acetyl-CoA. Here we have 7 beta oxidation cycles. We only get 7 acetyl-CoA, but we also get the propionyl-CoA. But if we're just considering our acetyl-CoAs, and then we consider the propionyl-CoA separately, we're going to have 7 turns of the TCA cycle. Going back to the beginning, we saw that per turn of the TCA cycle, we're going to generate a potential of 10 ATP. So we just multiply all of those numbers by 7, and we get that we could generate 70 ATP from that process. This propionyl-CoA, well, we just talked about what we could do with it, and we saw that it was going to take us, basically, we get a net of 24 ATP. So 25 ATP that we could generate from the oxidation, as well as considering the 1 ATP that we had to spend in order to convert the propionyl-CoA to our succinyl-CoA. So then we have our 24 that we enter here. And then if we take the net sum of all of this, what we find is that we can generate 120 ATP from the 17O fatty acid. And that's going to be more than we generated from our 16O fatty acid. And as we see, both of these are going to be really energy packed because if you think about a fatty acid, you have a lot of potential to oxidize it. With these oxidative reactions, we're going to be generating ATP, and the more oxidative reactions that we can go through, the more ATP potential there is. If you think about something like a sugar, it's good for quick energy, but it's got a lot of oxygens already, and so it's kind of already partly used. Whereas our fatty acids, they're going to have a lot of potential energy, a lot of chances for oxidation. And as we see, a lot of the energy that we get from our fatty acids is not directly in their breakdown, but it's in the oxidative phosphorylation that you get using the reducing equivalents that you generate from the oxidation directly of these fatty acids. So taking into account that NADH, that FADH2, those are really the big payouts, and will give you the big payouts if you consider the electron transport chain and your oxidative phosphorylation. So this is just a way to kind of help you think through the process. You could do this for any length fatty acid. You could do this for any other kind of metabolic thing that you want. I encourage you to do this for various processes. So if you think about glycolysis, gluconeogenesis, maybe amino acid breakdown, just make a table like this. You have the process, how many NTPs, NADH, FADH2, NADPH that you're using or that you're generating, and then taking into account oxidative phosphorylation. You can also make a simplified table where you can kind of just combine things. So just write in one box, like how many NTP you're generating, how many FADH, blah, 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 instead of spelling them out in different lines. So I encourage you to try it out. Start maybe with your fatty acid synthesis if you're into fatty acids. Deal with your glycolysis, compare and contrast, all this good stuff. Hope this helped, and happy studying.